Howdy, this is Jim Rutt, and this is The Jim Rutt Show. Today's guest is Jill Tarter.
Hi there, Jim.
Hi, Jill. Jill's an astronomer best known for her work on the search for extraterrestrial intelligence, usually shortened to SETI, S-E-T-I, an acronym we'll use a lot today. So remember, SETI equals Search for Extraterrestrial Intelligence. Jill is chairman emeritus for SETI research at the SETI Institute and was the inspiration for the Jodie Foster character in the movie Contact, based on the novel by Carl Sagan. Jill, here on the show, we've often discussed the Fermi paradox. It's actually become sort of a mini feature. Maybe half my guests, I've asked them what are their views about the Fermi paradox. Could you tell that story for us a little bit? How did it become called the Fermi paradox, and what is it?
Well, it shouldn't be called the Fermi paradox because there's no paradox. What it's shaped as is the supposition that any advanced technological civilization anywhere in the galaxy would very quickly develop the opportunity for interstellar travel. And they would therefore colonize the galaxy, no matter what model you use, in times that are short compared to the lifetime of the galaxy, which is 10 billion years. But it says, well, they're not here, and therefore the conclusion is there never could have been any time or any when another technological civilization, so we're the first. The problem with that construct is that we can't say that they're not here. And I really don't mean little green men abducting Aunt Alice off the city streets, but we actually have searched even just our own solar system so poorly that there's no way we could rule out the fact that there might be a small object stuffed with all kinds of intelligence, artificial intelligence in our galaxy, in our solar system rather, and we wouldn't have found it. And the same goes with the radio searches and the optical searches for signals. So poorly explored, our own backyard, that there's no way we can make a definitive statement they're not here.
When I was doing my research for this episode, I read an analogy. It might have been attributed to you, I don't recall, which said that all of our searches to date are considerably less than one glass of water taken out of the oceans of the world.
That's right. It's actually pretty full glass by now, but yes, just one glass.
No surprise that you don't get a fish if you pull a glass of water out of the ocean. So our audience has heard, lots of quite sophisticated takes on, why are they not here or why have we not found them question yet. And obviously that's what you've made most of your career. How did you happen to become involved with SETI search?
Well, it was just a very fortunate accident. My first year in graduate school at Berkeley, we got our first desktop computer. Now, at that time, it took 2 people to get it onto your desktop. But it was a PDP-8S, and there was no programming language. So you had to program the whole thing in octal. You had to set all the ones and zeros. And I learned that skill in order to program a spectrometer at an optical telescope that the university used for teaching. And many years later, as I was getting towards the end of my graduate career, this computer was given as a piece of surplus gear to Professor Stuart Boyer, who had a very clever idea about piggybacking on the university's 85-foot radio telescope in order to do SETI searches at the same time that other astronomers were doing more traditional radio astronomy. It was very clever. He just had no money to pull it off, and so he went begging, and people began giving him things such as this old computer. And he came to my office with a copy of the Cyclops report, the results of a summer study design workshop that was looking at what you might do to detect extraterrestrial intelligence if you had unlimited funds. And he gave me the Cyclops report as a recruiting document and wanted me to join his team so that I could program this old computer for him. And that's exactly what happened. I mean, I read that Cyclops report and I thought, my goodness, here I am at just the right time with just the right skills, an undergraduate degree in engineering and a Ph.D. in astrophysics. And here's this fantastic problem, this question that we've been asking ourselves forever. And I could do something to contribute. So I got hooked. And I've stayed hooked.
Wow, that's so lucky. Because, when I think about the big questions in science, and that's something at the Santa Fe Institute, where I've been affiliated for the last 18 years or so, we try to do. What are the big questions? In my own ranking, I put the SETI question as number 2.
And what would be number 1 for you?
And number 1 is, why does this universe exist? And after that, I think SETI is number 2. And of the two, I think SETI is the more likely to be accessible to an answer in a reasonable time frame and a humanly potential level of effort. But I also think it has a gigantic moral component, which I often don't see talked about. Because at one level, if the galaxy and the universe is relatively abundant in intelligent life, then that means we're one of many. And while we have a duty to protect ourselves for our own purposes, we probably don't have a higher duty to the universe itself. However, should it turn out that we are alone? And it's funny, when I was a 12-year-old nerdy guy who, stumbled upon astronomy and the Drake equation and such, I must have been right new at the time, I said, oh, of course, there's got to be plenty of intelligent species in our galaxy alone, let alone the universe. But as I've done more reading on it and I've thought about it hard and my own learnings in complexity science and information theory, it's at least possible, to my mind, that we might be alone. And if we are, then we have a huge moral duty to the universe, which is to bring the universe to life. I would say that life is fundamentally more interesting than non-life. And if after a very extensive SETI, say, 1,000 years at $10 billion a year, we were to conclude that there were no other life in the universe, it would seem to me that the mission for humanity ought to become to bring the universe to life. So that's why I think this is such a hugely important question. And yet when I was researching your career and the whole SETI field, I was flabbergasted by what a struggle it's been for even the most inconsequential funding. It's like, it's madness. What do you have to say about that?
Well, I think it is madness. It's been an incredible roller coaster for all these decades. We have now Mr. Milner, who's taken on responsibility for searches in this decade, which is great. But we always need more money in the field. And I think we should get back in the federal domain as well. So the thing that I really enjoy having the opportunity to do is talking to audiences such as yours and getting to think about these bigger questions, getting them to think about themselves as compared to something else that's out there. And if I can get them to engage seriously with the topic, then it has the effect of trivializing the differences among humans, because compared to something else out there, we're all the same. And I think that cosmic perspective is incredibly important over the coming decades to help us manage the various challenges we face with climate and water and food production. And these are challenges that don't recognize national boundaries. We're going to have to solve them globally. And so if I can help other humans have this larger point of view, this cosmic perspective, I think that goes a long way to finding the answers we need.
I hadn't thought of that. That's a very interesting perspective, and certainly particularly relevant in our current time when it sort of seems like tribalism is making a big comeback, unfortunately. And having that distance, saying, on the scale of the cosmos, the difference between a Sunni and Shia is utterly inconsequential on the scale of the universe. So why are you slaughtering each other, right? Let us realize that we are, heck, all life on Earth is probably very close cousins compared to anything we're going to discover in another tree of life elsewhere. And that's a wonderful perspective. I think that's a very, very healthy idea to put out into the world. Let's switch back now to SETI science a little bit more directly. The Drake equation has long been the touchstone for thinking about SETI. Could you take us through it and maybe tell us the points in the Drake equation and maybe even a little bit about what we know about them?
Sure, but let's start out with the fact that the Drake equation is actually a great agenda for a meeting, but you can't calculate anything with it. There's just too many unknowns. But Frank Drake, when holding a meeting on this topic way back in 61, did put together an agenda, and he thought about all of the factors, the things that you would have to understand in order to try and estimate the number of communicative civilizations that could be out there in the Milky Way. And he started with the rate of star formation, because we think stars are needed to have planets. And then he wanted to know the fraction of stars that actually had planets. Now, remember, it's only been the last decade or so that we know about planets around other stars. Back then, we had no clue. And then he asked, well, in a planetary system, what's the average number of planets like the Earth that could be habitable? And in our solar system, he would have said 3. Mars, Earth, and Venus might have been good ideas for life. And then of those good planets, what fraction of them actually does life begin on? And of all the life starts, what fraction of those develop intelligence? And of the intelligent species out there, what fraction of them develop a culture and a civilization? And lastly, how long does that technological civilization last? Because if civilizations arise, develop technology, and do themselves in or turn themselves off very quickly, there's not likely to be anybody that's going to be close enough and co-temporal with us, that is around at the same time in the 10 billion year history of the galaxy. So he multiplied all those factors together and put in his own favorite numbers and came out with 10,000. And people have been arguing about the numbers ever since. A couple of summers ago, the folks over in Oxford, who love Bayesian calculations, looked at all the literature on this topic and said, within the literature, for the fraction of planets that actually life starts on, the probability of abiogenesis, they said there were 120 factors of 10 difference in numbers that people ascribed to that factor. In a sense, we have no idea. And a long time ago, Philip Morrison told me, he's a pioneer, one of the pioneers in SETI, told me that any topic where the error bars are in the exponent is a topic that isn't going to yield to theory. It's one that's going to have to be solved or understood observationally or experimentally. And I certainly believe that's the case with SETI. We can sit on a mountaintop and stare at our navels all we want, think about it, but what's going to answer this question is observation.
Yeah, at least until we have more data, and and it's kind of a bootstrap, like as you pointed out. Actually, I laughed when I went back and looked at the Drake equation. It was clear that must have been stated when the steady state theory of the universe was still in play. The way he talked about planetary formation, I thought was interesting. If it had been clearly in the absolutely Big Bang side of the world, he might not have stated it quite that way. And also, as you pointed out, we had no clue about the number of planets. I remember from my elementary school science books, they were still arguing, did planets come from the disk around the star, in which case they would be common, or was it the result of a very rare near collision between two stars, in which case planets would be rare? I think we now know that it's the first, that it was from the accretion disks around the stars, and that probably essentially every star has planets. So there's some real data.
The Kepler spacecraft and the ground-based observations of the last decade have, in fact, ensured us that there are more planets than stars in the galaxy.
Yep. And, clearly on very much on the high side of what people might have thought. So that starts to tune in the Drake equation or a replacement for it. And then think about other things that we will be learning in the next 20 years. Is biogenesis exceedingly difficult or is it relatively common? I think we'll have a few clues. One, when we get out to the outer planets and their satellites, we'll be able to dip into Europa and some of the other possible sources of life. And if we can find a completely different tree of life than ours, that probably tells us biogenesis isn't that hard. In Mars, we may find a separate tree of life. Though I got to say, my guess is if we find life or residues of life on Mars, it would not at all shock me for us to have found that our life actually started on Mars and came here on a lucky hop. But we do have those kinds of items of data coming up. And then the next thing we have coming up are the atmospheric studies of the exoplanets, right? Where we'll be able to look at constituents of the gases in the exoplanets and look for signs of life. And each of those will start to bound some of this uncertainty.
Right. But the biosignatures search that you're talking about in exoplanet atmospheres is going to be very nuanced. There is no smoking gun that we've been able to postulate yet. And so it's going to be very much a result that depends on context, the age of the stellar system and the planetary system and the location relative to the star. And if you think about the Earth's atmosphere, early in its history, our Earth's atmosphere was dominated by methane coming from methanogens. But then we had 2.4 billion years ago this great oxygenation event when blue-green algae figured out how to do photosynthesis and produce oxygen as a byproduct. And then we changed the atmosphere completely. And so while there was life on Earth in both of these variants, the atmospheric trace gases were completely different. So understanding the context for the planet's evolution is going to be necessary and very hard to do as we make the spectroscopic searches for various trace gases.
Yep, it'll drive, thinking about the theory of how the Earth evolved as well at the same time. As you point out, to the degree that we can reason from our own experience as a planet how our atmosphere evolved over 3.5 or 4 billion years, we may provide us some models which would say that atmospheres that look like this are probably biotic, and atmospheres that look like that maybe not. For instance, at least something I read said that a mixture of oxygen and methane within certain ratios may be a pretty good indicator, pretty good biomarker.
Well, it's actually an extremely good indicator of chemical disequilibrium. And on our own atmosphere, it's 100 times out of equilibrium. So what you'll see, methane and oxygen, you'll see this strange chemistry that's out of equilibrium. So something's forcing it. But is that something biology or geology? There are ways to get oxygen that are abiotic, right? And we don't know the limits of how much out of equilibrium you can force something without the presence of biology. It's just something we don't yet know.
Do we have any ideas about the difficulty of same? For instance, once we have a substantial body of atmospheric surveys, let's say 1,000, and if we see the oxygen-methane combination being, let's call these water zone planets, we see it being fairly common. Are any of these geological mechanisms plausible enough that they would be common across this body of planets, or does a high frequency of that signal tell us something different than a single occurrence of that signal?
Yeah. Well, is it telling you that life is everywhere? Or is it telling you that it's geologically not too hard to get this disequilibrium? I don't know. We don't know.
Interesting. Because I must say, when I think about the ways that we might be alone, many of them do come to the earlier stages of biology. How hard was biogenesis, and right around the transition when this is amazing conversation I had with Stuart Kaufman many years ago, and we talked about the fact that in evolutionary theory, if you don't have high fidelity information transfer between generations, you run into something called the error catastrophe, where the ability to build up structure is very limited. But once you get to high fidelity information replication, such as we have in the DNA architecture of even the most primitive bacteria and archaea, then evolution can work. And then you sort of ask yourself the question, without high fidelity information, how in the world did the earliest archaea or bacteria or whatever their common ancestor was manage to develop this rather complicated machinery for duplicating DNA? And you go, quite a puzzle. Might have been really, really unlikely. So, that's one of these things that as we learn more about the origins of life, maybe we can strike that one off the table and say, nope, that wasn't that hard. Or we can say, yep, that was extremely difficult. The next one on my list is apparently only one time the creation of the eukaryotic cell, where a bacteria absorbed an archaea, or the other way around. One of them became the cell, one of them became the mitochondria, and that increased the energy density of living cells by a factor of 10,000, something like that, or I guess the gross energy of a cell by something like a factor of 10,000. If that happened only once in 4 billion years, it doesn't tell us much about whether it's one in many, many more years or what.
Yeah, too bad Lynn Margulis isn't still around. I mean, she had such a hard time getting the scientific community to accept that model. So symbiosis is not something we were prepared to take on Lynn's word. It took a lot of hard and painful operations on Lynn's part to get this notion across and accepted.
And as far as I know now, it's accepted by everybody.
Yeah. Yep, it's a good idea.
We do a lot of tracking of genetic evolution through the mitochondrial DNA, right? Because we want to go down the maternal line and say, all right, this is what the maternal ancestry looked like separate from the paternal ancestry. And, as far as I know, it's just taken as reality now by everybody working in the field. Okay, let's turn a little bit from the science and the Drake equation to policy. One of the things I came across in my research was something called the first SETI protocol, basically a protocol for what we do if we think we have a signal and we are starting to verify it, et cetera. Could you tell us a little bit about that?
Sure. That protocol was written back in the 80s during the height of the Cold War. And it was written under the auspices of the International Academy of Astronautics, which has had a standing committee on SETI for many, many decades. And back then, some of us were concerned that our colleagues in the Soviet Union who were doing SETI searches might succeed in a detection, but be prevented from making that information public. And so we wrote this protocol as a way of encouraging everybody who was operating and doing SETI searches to have kind of a standard way of behaving given success. And it basically said, you need to verify with your own instruments that what you think you found is what you think it is. You need to try and get independent confirmation quietly without making a big fuss, so that you can guard against intentional hoaxes. And then you need to tell the world, right? And at least for the signatories of that protocol, signatories, we agreed that we would not broadcast a reply until there had been some international consensus that we should do so, and a decision about who would speak for Earth and what would be said. So totally idealistic, completely unenforceable, but written with the best of intentions and hopefully to give our Soviet colleagues some backing when they wanted to make an announcement if they ever succeeded.
Is this protocol still a live letter in the SETI community? I mean, are new young researchers aware of it? And is it part of their acculturation into the SETI researcher culture?
Yes, it is. It's being updated the last time about 5 years ago by the International Academy of Astronautics Permanent SETI Committee. And I think that many young people who are joining the field get told about this very early on. What would I do if I got that signal? Oh my gosh, we've had a couple of false positives over my career, and it's just a huge adrenaline high.
I can't even imagine what it must be like. I mean, because it's like, as I said, it's the second greatest discovery possible, right? And you go, oh my God, is this it? Right? Have you personally been involved in one of the strong false positives?
Oh, yes. I was involved at Green Bank, West Virginia back in 1997, 98.
Would you mind telling us that story? That'd be hair-raising for me, at least.
Yes, well, around 5 o'clock in the morning, I detected a signal. And if you think about what it might have looked like, the spectrum looked like a picket fence. That is, there were narrow band signals, strong, and separated by a particular spacing, and many of them. So it really did look like a picket fence on our waterfall display. I did everything I could think of. I pointed the telescope. The beginning of the story actually starts a few days before. We always did our SETI observing in Project Phoenix with 2 telescopes, widely separated by hundreds of miles. And we did this because we were looking for narrow band signals, which our technology produces quite a lot of. And the trick here was that if you use 2 widely spaced telescopes to observe a particular target, and you saw the signal in both of them, the signal would actually show up at a different frequency and different drift rate slightly in the 2 telescopes because of the Earth's rotation. There would be a differential Doppler signature.
Makes perfect sense, yeah.
It was a really good way to filter out our own technology. So, lightning struck the telescope, the second telescope in Georgia. And we still had the 140-foot telescope in Green Bank, West Virginia, and we had time. And so we continued observing, and all we could do to try again to discriminate against our own technology was to look at the star and then look off the star. And if it's really coming from the star, then we should see it when we look on and we shouldn't see it when we look off. Anyway, because of a lightning strike, we lost a disk drive of the telescope at Georgia. It took FedEx a few days to get a new one in there to repair it. And we kept using the telescope at the National Radio Astronomy Observatory in Green Bank, the 140-foot, and we point at the target, and then we point off the target, and then we come back and look at the target. And we should see a signal that's really coming from a distant source on the sky when we looked at it, and it should go away when we looked off the star. And so we did that with this signal, and every time I pointed at the target, the signal was there. Every time I pointed the telescope away, the signal was gone. This looked like a really good bet, and we started doing all of the things that we had planned, like reloading software to make sure that somebody had not put a signal into our software. And I woke up my colleague, and we tracked that star for another few hours until it set. And the signal was always there when we looked in the direction of the star and never when we looked away. But we did notice that, in fact, the Doppler shift and drift were appropriate to a source that was rising to the zenith rather than setting in the west. And so we knew that it really wasn't coming from that distant target. And at this point, we had also alerted our colleagues in California, and they had a model or a copy of our observing system, and they were watching what we were doing. And they were very excited, in fact. And so we all went off to dinner at Green Bank having made this discovery that it really wasn't a signal from extraterrestrial intelligence. And we forgot to tell our California colleagues. So they stayed up until about when the target rose again, expecting to see a signal. And I had a lot of fence rebuilding to do when I got back to California. They were not pleased at all. And as soon as I saw what the parameters of this signal were, I wrote some code to interrogate the database that we keep on all signals that are detected, to ask the question, had we seen this signal structure before coming from some different direction on the sky? That was a clever thing to do, but I was so excited. I mean, adrenaline was really unbelievable that I didn't take very much care in formatting my output. And so when I looked at the output, I missed the fact that indeed we had seen this signal before from another direction. We could have saved ourselves a day of excitement if I'd been careful and not so excited that I screwed up. Anyway, for me, that was probably the most exciting false positive that we've had.
It was actually a good proof that your protocol is well designed, right? Because despite the fact there are a couple of errors in the process and bad luck of having your second observatory down, you still didn't put out a false announcement, which I would say is a sign that your processes were good. Because that's in human affairs, especially catastrophic problems often come when multiple things go wrong simultaneously. So here you had several, right? Or at least two. And nonetheless, you protected yourself with a well-designed protocol.
Or I got lucky.
Yeah, or you got lucky, right? Or you got lucky. Well, and lucky, I'll take lucky. Luckily, if you have your choice of lucky or smart or lucky, go for lucky every time.
Yeah, well, in fact, it was not completely kept quiet. By accident, I had been scheduled to fly out back to California at the noon on the day that I found that signal in the morning. So it was too early in California to call my husband and say, I'm going to hang out here for a while more. So I called our administrative assistant and left a voicemail for her saying that I wasn't going to be coming home that day. And would she please tell my husband? And then during the day, Anne Durian, Carl Sagan's widow, called to discuss something with me. And Chris said, oh, well, she's staying in Green Bank a little longer. And from there, it went to somehow Bill Broad at the New York Times, who called up our colleagues in California and said, here, there's something interesting going on. Do you want to talk about it? And Seth Shostak told him, well, no, give us another 8 hours and then we'll talk to you. And he was good enough to do that, to call back 8 hours later. And we had to say, sorry, false alarm.
Amazing how a tiny signal was able to propagate out to the New York Times, but that's the way of the world. Imagine today with Twitter. Oh my goodness, even the slightest link would likely get magnified 1 million times.
Yes, that is why the protocol needs to be updated. And in fact, we took on an exercise called revising the Rio scale. So in 2000, Ivan Almar and I gave a paper in Rio de Janeiro, hence the name Rio scale. And we tried to come up with a numerical scheme on the order of 0 to 10, like a Richter scale, that one could assign a potential signal detection so that there would be some easily remembered way of saying how important this was, how impactful this particular detection was. And the 0 in that scale is really important because that's what you give a hoax. And there are many people who enjoy publishing the fact that they have detected signals and the evidence is just not there. So we did that in 2000, and then just last year we revised it in lieu of the media and the way that we communicate information today. And so it's now a website, and you can take a look at how people are ranking that putative detection and how the detection either becomes more crystallized and confirmed or fades away because the evidence just don't support it.
I'm finding the Rio scale on the SETIleague.org website. Is that the best place to check it out?
That's an easy place to check it out, yes.
So for our listeners, type in Rio scale and pick the link that goes to SETIleague.org.
Jim, that's the original one. I haven't checked that site in a while. They really should search on Rio 2.0.
In this world of, as you say, the hyperactive media, this is all really important stuff because there are lots of malicious people out there who would get a big giggle out of doing a false SETI alarm. Let's get back to our topic list here. Binary stars. What's the current thinking about whether they might be suitable for life and or advanced civilizations?
Right. Well, if you remember Tatooine, the system from Star Wars, double star system that Luke Skywalker grew up on, a planet around that double star system. We've actually found planets around binary stars. And Lawrence Doyle from the SETI Institute was the one to recognize the first such star systems in the Kepler database. It's interesting. There are two configurations that we think might allow for habitable planets around binary stars. One is if the binary stars are very close together and you have an orbit maybe 7 times or 8 times as big as the separation between the stars. So the planet would circle both stars. And the other configuration is widely spaced binaries, where you can have a stable planetary orbit around one of the stars. And both cases seem to give us, at least in terms of simulations, habitable conditions. And whether or not the planets that are around such stars actually are inhabited, that's our next question.
Interesting. And it was still thought that perhaps a majority of stars are in binary or more star systems. Is that still the evidence from astronomy? Okay, so that's important. Next question. How far away could we, with our current level of detection, detect Earth's intelligent emissions?
Sadly, not very far. Certainly the television leakage, which people always point to and say, oh, the aliens are going to discover us with howdy doody. Not so far, not even to the nearest star. But if you talk about our strongest transmitter, which is a 2 megawatt radar of the Arecibo Observatory, so you've got 2 10 to the 6 power transmissions and a gain of 10 to the 7. So you've got a few times 10 to the 13 watts of power in that beam. That's detectable very far, sort of halfway to the galaxy center. And the only problem is that beam is incredibly narrow.
I was going to say it's not a spherical wave. It's just a tiny little cylindrical.
It's like a pincushion, sort of. Yes.
So that's interesting. How about say more powerful than TV? Military radar or something like that.
Yes, you can get a few light years.
So truthfully, if they are out there, they haven't seen us unless they have a lot better detectors than we do, which is, of course, possible.
And actually, it's probably probable because most of the stars in our neighborhood in the galaxy are about 1 billion years older than the sun. So they would have had a head start, quite possibly. And, technology. So we don't know. There are kind of 2 models for technological growth. One is the sort of S-curve that we see in all sorts of biological and engineered systems where you have nothing and then you get an exponential rise and then you saturate some resource. So your growth turns over. And then the other is you have nothing and you start an exponential rise and it just keeps going. We don't know what the future will be for technology, whether we use up some particular resource, whether we decide to turn inwards the way the Chinese did by burning their ships on the beaches and ceasing from the exploration that they had been doing. We just don't know. But in any case, the probability is highest that you will find that technology in an old phase rather than at their early stages. So it's not unwise to expect some more advanced technology than we have. Indeed, Arthur Clarke had 3 laws. The first one, when an elderly scientist tells you something is possible, he's almost certainly correct. When he tells you something's impossible, he's almost certainly incorrect. The second law is the only way to understand what's possible is to push beyond into the impossible. And the third is any sufficiently advanced technology would be indistinguishable from magic.
That last one I really like. And, again, it might be one of the conditions where they're there, but we just can't see them because the way they communicate from our perspective is magical. We can't even imagine. Maybe they manipulate gravity waves or something, right?
And so there's been recently a variant of that third law. Carl Schroeder, a philosopher, environmentalist, has said that any sufficiently advanced technology will be indistinguishable from nature.
There was actually a paper written by David Wolpert and a couple other guys that indicated that the most efficient communication system using electromagnetism is very likely to look like noise, right? That it's so sophisticated and so compressed that if it was not a beacon to be found, we may well mistake it for nature.
That's right. And I think a lot of us are excited at the moment about putting some neural networks into our signal detection programs so that instead of us telling the machines to look for a particular type of signal, one that we think is obviously engineered and that nature doesn't produce, we're hoping that with trained neural networks, we can allow the machine to tell us whether there's something other than noise in the data.
That would be a very good use of machine learning. I mean, machine learning is perfect for that kind of problem where you're looking for statistical anomalies that, irrespective of whether humans can imagine them or not, which is actually very similar to how AI is evolving. It's an area that I follow very closely. And, good old-fashioned AI, basically a bazillion if-then statements that were limited by how smart the graduate students were. Now we have machine learning that is able to find things that no infinite army of graduate students would have ever found by doing inferences from unbelievably large data sets. Seems to be a very good fit for the SETI program. So I would definitely think that makes a lot of sense. Another science question. There's been a lot of development in the last 20 years around extremophiles, forms of life on Earth that have been discovered in unbelievably hostile environments. And that would seem to speak towards, at least say something about maybe the range for which life could exist is wider than we think.
Absolutely. So over my career, the exoplanets and the extremophiles have been the two real huge game changers. And, we say they live in hostile environments, but it's only hostile to us. They've evolved to be fat, dumb, and happy in those environments. And it's just a surprise to us. We have this wrong attitude. We talk about the ascent of man, and we talk about humans being the pinnacle of evolution. Well, that's a perspective that just isn't borne out by nature. We are just one little trig, and there is an amazing abundance of life in environments that when I was a student, I was told were sterile. They've never been sterile. We just haven't been open-minded enough to find them.
I understand things like battery acid, deep under the Earth's surface, just in amazingly harsh environments.
That's right. And some of these, like radiodurans, incredible tolerance to very high temperatures and desiccation. It actually has ways of repairing its DNA that are not something that humans do. And so one of the things that's been fun at the SETI Institute is that we now have researchers from the medical profession coming along on expeditions to study extremophile sites because they're wondering what they can learn that might be beneficial to human health by studying these extremophiles.
Very interesting. As you say, that's another one that's, I would say, argued in favor of SETI, extremophiles, and as you say, lots of planets. Two good things probably on the equation. Though we're still out in twiddling with the exponents, so we still don't know. Next question. A lot of your work in particular has been around signals, but there's also other possible ways to detect SETI, or at least past SETI, what people might call artifacts. Remember the stories about Tabby's star or the possibility of Dyson rings or Dyson shells. Could you tell us a little bit more about that?
Well, SETI, first of all, is a misnomer and always has been because we don't know how to directly detect intelligence. What we're doing is using technology as a proxy. And if we find the technology, we are going to infer the presence of intelligent technologists, at least at some point in time. So we've begun using a term that's technosignatures. It parallels the biosignature work looking for evidence of any kind of life, microbes. We want to look for the mathematicians, so we're looking for technosignatures, anything that would be a change in the environment in a way that you could sense over interstellar distances. So the Dyson sphere discussion or megastructure discussion that was going on with respect to Tabby's star is one such technosignature. And what we're doing is we're thinking about the new telescopes that are going to be coming online in the next decade or so for astronomical research. And we're thinking, okay, what might those telescopes see that would be an indication of somebody else's technology? So an example that I like to talk about is the TRAPPIST-1 system. This is a system with at least 7 planets. orbiting a little red dwarf star, and their orbits are so tight that whole system would fit within the orbit of Mercury around our star. But even though the orbits are tight, they are still at different distances from their host star, and therefore should have different equilibrium temperatures. But what if we took a look at that system with some of these instruments that we'll have in the future and discovered that 3 of them were identical? Even though they're at different distances from their star, they had the same equilibrium temperature, they had the same kind of chemical structures in their atmospheres. To me, that would be suggestive of somebody else's engineering on a very large scale. And so that would be a technosignature.
Yeah, very clever. I like that one a lot, actually. And again, if you only have a small number of systems you look at, well, who the hell knows? But if you have a bunch of them and have a bunch of them with that signature, then you're starting to think about maybe we have a high frequency pattern here. On the other hand, one of our previous guests on the Jim Rutt Show, Robin Hansen, who's I would say a SETI pessimist, his argument was that inevitably any really advanced civilization ought to show a giant shift of its energy from its star to the infrared as it starts to use more and more of its star's energy. And yet he argues, and I will say he's an economist and a raconteur, not a physical scientist. He claims that we should have already seen such large-scale red shifts if there were a lot of advanced civilizations, even in other galaxies. How would you respond to that?
Well, indeed, Jason Wright and his colleagues at Penn State University have done exactly such a search, right? They've used the data from the WISE infrared spacecraft that surveyed the entire sky, and they have looked, first of all, for technology on a huge scale, so-called Kardashev-3 type civilizations, which are able to manipulate the total energy output of their galaxy. And they've looked for these infrared signatures from galaxies. That was the easy part of the search. And then now they are looking at stellar sources and looking for infrared excesses in stars. That's a lot harder because of the confusion limit in the observations. But it's something that's been thought of. And in fact, people are trying to do it.
Glad to see that they're probing on all these theories. Now, we've kind of talked about the past and the theoretical bases, et cetera. What's really going on right now? What are the big efforts in SETI right now? I know there's, you have your Allen telescope array from the SETI Institute, and then the guys at Breakthrough are buying time on radio telescopes. Tell us about some of the projects that are actually ongoing as we speak.
Well, the Breakthrough Listen team at Berkeley is renting time at Green Bank in West Virginia, and the new telescope there, 100-meter telescope. They are also renting time at Parkes, New South Wales, and they are looking at building instrumentation and backends for a new telescope called Meerkat in South Africa. Ultimately, we hope this equipment will be on the Square Kilometer Array when that gets built. They have memoranda of understanding with the Chinese for instrumenting the FAST, the new radio telescope in China. They are also looking towards Jodrell Bank in the UK, and they will be increasing their efforts, getting their very beautiful back-end equipment onto telescopes around the world. We also have some optical SETI projects, in particular one that I'm really excited about is being done at the SETI Institute. It's called Laser SETI. And the idea here is that with 12 sites around the world and 8 cameras at each site, we could be looking for optical flashes, optical SETI on all the sky all the time. And if you're looking for something transient, this is what you want to do. We knew that back in 2000 when we wrote the SETI 2020 report that said what we should be doing for the next 20 years. And looking for transients, looking at all the sky all the time at as many different frequencies as we could, was something that we realized we should be doing. But until now, we have not had the technological capability to do so. So this will be the first truly all sky, all the time observatory for SETI. The first cameras have been installed now at the Robert Ferguson Observatory up in Sonoma County. And the next one will go to Haleakala in Hawaii. Then there's another optical SETI program that is being worked on, PanoSETI. And the idea here is, if you remember the Buckminster Fuller domes, well, you fill each of those segments on a dome with a big plastic Fresnel lens, and then you focus a large piece of the sky on a small infrared detector. So you build a telescope that has something like 120 different beams, so looks at a number of square degrees. I think it's, I don't have my notes in front of me, I think it's 8,000 square degrees, and does this same sort of observing for flashes. And then you build a second one of these a little bit away, right? That's sounding familiar from Project Phoenix, so that you can get confirmation of anything that's detected. I mean, you see something flash once and, well, gee, what was it? Was it our instrumentation, or was it something really there? But if you have a second one of these, you can get confirmation. And I'm excited to see that go forward. And then we're thinking about, all of these wonderful new telescopes, the TMT that will be built somewhere, the LSST, the very large optical telescope being built by Europe, and perhaps in the radio, the next generation VLA and the square kilometer array. And so we've been thinking about how we can get signal processing in parallel with these telescopes, how we can use them to do SETI at the same time that radio astronomy is being done. And so something is happening right now at the Very Large Array, the radio telescope in the Southwest. And we are essentially building a spigot that can take data being observed by anyone for any purposes, and that spigot makes the data available to SETI detectors. So the breakthrough team will be building a back end to swallow data from that spigot so they can be on the air essentially all the time. And this goes back to the first project I ever did with Stu Boyer, Serendip at Berkeley, which is saying we can't decide where the telescope is going to point or what frequency it's going to observe at, but it will give us a whole lot of time on the sky. And, at some level, we don't really know where to look anyway. So we might as well just look where the astronomers are looking. And so this back-end device for the VLA should be up and running in a year or two. And that's going to be an exciting opportunity because that's a very large telescope.
And of course, you have Moore's Law working for us. Back when you're PDP-8, you would have had no hope to process all that data. But today, with many generations of Moore's Law increasing the amount of transistors and driving the costs down, we have almost ubiquitous computer processing to do things like machine learning on all this data.
Yes. Thank you, Gordon Moore.
Absolutely. Okay, let's move on to the next topic. And this is where we get into some controversy. METI, the idea that perhaps while we continue to listen, we ought to step up and broadcast. In fact, my next guest on the Jim Rutt Show, David Brin, has very strong views about METI. I wonder what your thoughts are on whether we should be first tell the audience what it means to be broadcasting versus listening, and if you have views on whether that's a good idea or not.
Well, I do. They're a little less extreme than David's, but METI is this idea of messaging extraterrestrial intelligence, that if everybody is listening and no one is transmitting, that's not going to work. So we should step up to the plate and transmit to allow other advanced civilizations to know that we're here and interested in communicating. And my problem with that is that we barely manage as a species to get through 2-year plans. Very occasionally we get through a 5-year plan intact, but we're not set up to tackle 10,000-year plans. And the thing about transmitting is if it's going to make any difference, you have to start and not stop. Because if you transmit for 5 minutes, your signal is going to go whipping by your target in 5 minutes. And they would have to be looking at you at exactly the right time with exactly the right tools to catch that signal. And then they're going to be a little bit wary about whether that one shot was really something or something they can't explain. And so I think that transmitting is a long-term project. And we're just not grown up enough yet as a technological civilization to do that. When we are, I think we ought to take on the role of transmitting. I often think that perhaps, and again, it's just my thoughts, perhaps the distribution of intelligent technological civilization ages is bimodal. There are a lot of technical civilizations that pop up and don't manage to last very long. But there are some that do make it through any kind of a filter to an old age. And I wonder if transmissions, the detection of a transmission from another technological civilization, might not be the distinguishing characteristic about whether you tunnel through from the very young and make it to be an old civilization. So I think there is potentially, as we become old and stable, there might be an onus on us to help others get there too.
Although we seem to be a very long way from old or stable. I mean, truthfully, the modern world's only 400 years old, and I put the start of modernism at 1625, right? And so on the scale of the universe, we are not an old society at all. We're not even an infant, or hardly, right? We're still a fetus.
So I think at this stage in our development, we do the easier thing first, which is listen.
Are you concerned about some of the, precautionary principle type arguments against transmitting, the David Brin or Stephen Hawking ideas that, hey, maybe the universe or the galaxy is full of predators and it'd be damn stupid for us to announce our presence?
Well, why does that worry us? It worries us because we think they might show up on our doorstep and have us for lunch, right? But think about it. If they can get here, we can't get there. But if they can get here, then their technology is a lot more advanced than ours. They probably already know about our existence because of the ways that we use the electromagnetic spectrum. And they're going to write the rules one way or another. And I actually think, unlike Stephen Hawking, I actually think that there might not be any reason to have fears about this happening, because if they can get here, then they are truly an advanced technological civilization. And I think perhaps the stability that age implies would argue that they have had to outgrow the really pugnacious tendencies that they might have had earlier in their evolution. Because if they haven't, I don't think they can become old and advanced. So it's kind of the Steven Pinker kinder and gentler argument of cultural evolution.
That's certainly a hopeful way to think about it. And if we were to find such a civilization, the things we could learn could be unbelievably huge. One would think, a civilization 1 billion years older than ours, able to navigate between the stars. It'd be very surprising if we didn't have something to learn from a civilization like that.
Agreed. And we probably don't have a lot to offer them except our uniqueness as a species. So that's my philosophy, but I'm an optimist by nature.
Yeah, I wonder, be very interested to hear what David Brin has to say on Monday about this. But as I understand, he has other views. So that's why we do the show, get all kinds of different views out there. Let's move on again a little bit. I read a recent paper, it may even have been in draft, by someone named Jason Wright. And by his calculation, the federal government is currently spending 260,000, that's 1,000 people per year on SETI. I'm going, that's nuts. That is nuts. What is the problem with our science that to address the second biggest question in science and the biggest one that's accessible at this point in time, that we would be spending something considerably less than the bagel budget for one small agency to answer this question? Do you have any idea? What is it about SETI that is repugnant to federal funding?
Well, my opinion, and again, it is an opinion, and I concur with Jason's numbers, is that it's fundamentalist religion. There is an element of our Congress whose constituents think that we on Earth have a unique and special relationship with Jesus Christ, and that is not consistent with other technological civilizations all around the place. So when you ask the world's major religions about the question of life beyond Earth, they have no problem with fitting this into their dogma. But when it comes to the fundamentalist Christian religions in this country, some of them do find this extremely upsetting. And that reflects on their representatives.
We think there's enough pressure just from that, kind of fringe early Earth, young Earth people to be able to actually prevent the allocation of appropriate level of funding?
Yes, well, the NASA's SETI project was canceled by one senator. It was done in such a harsh and deliberately punitive fashion that, SETI became the four-letter S word that you couldn't say at headquarters for, since 1993. And we're now talking again about the potential of searching for technosignatures as well as biosignatures in the astrobiology program. And we're looking at trying to get back into federal funding, but I don't know if we're going to be successful. As I said, it's been a roller coaster.
Drives me crazy to even think about this, right? If I were the philosopher king, I'd allocate at least $2 billion a year to SETI, something on the order of 10% of the NASA budget. Why wouldn't you?
I can take the other side and say that you wouldn't allocate huge amounts of money. You would allocate money in a way that is continuous into the long future. The point is, we may be doing an incredibly fabulous job at exactly the wrong thing. We may not yet have invented or discovered the appropriate technology for interstellar communication. So we ought to fund this in a way that is dependable and consistent, something like an endowment at a reasonable level, but not a huge level. Because when you talk to young people and you try and encourage them to come into the field with all their new ideas and talents, it's a bit fringy. But if you have to say to them at the same time, well, not only is this a bit off the mainstream, but I may not be able to cover your salary next month, that becomes a real challenge. And we do want the best and brightest of the young scientists and engineers coming in to enhance and improve this field. But we need to be able to say, and yes, you can raise a family too.
Yep, absolutely. If you were the philosopher king of America, what would you think is a reasonable expenditure rate on, maybe even an unreasonably aggressive, but not insane level to spend on SETI per year?
We've taken a look at that question and seen what we know is in the pipeline, what might be coming down. And I would be doing $20 to $30 million a year.
Unbelievably tiny dollars on the scale of our federal budget. And a few religious nuts are preventing this from happening. This really annoys me.
It's not been an easy ride. And I may be wrong. That may not be why it was terminated, but it certainly, we got indications that that's what Senator Bryan was about.
Well, you certainly were at the center of it more than any other human on earth. You are one of my great heroes for having dedicated your life to this project, which I believe to be of the utmost importance and yet has been not given anything like the support and respect that it deserves. So I will take your word for that as a very likely possibility of why this has been not funded appropriately. $20 million, people, my listeners out there, call your congressmen, call your senators, tell them that a tiny amount of money, probably the cost of 3 flashlights and a hammer for the Pentagon, we could have a program that would make Jill Tarter happy for SETI to answer the second biggest scientific question that humanity confronts. This just drives me mad that this is not happening. So maybe our audience can help make this happen.
I'd love that. But the mess has to be next year and the year after that and the year after that, et cetera.
Make it a long-term commitment, a 100-year commitment, right? I've seen in some of the things I researched that you've proposed thinking about that way. Over 100 years, we could look X light years out, Y number of stars, and then now we could have these other technologies, laser SETI versus artifact object looking versus radio frequency listening, and one could essentially build a series of cells and fill them out over 100 years, right? And at that point, we can say, all right, this is what we've learned. Here's our Bayesian. Here's our new Bayesian, right? Here's our prior. Here's what we found. What do we think now based on 100 years worth of research? And again, 100 years is nothing in astronomical time. If it takes us 100,000 years, it's still a search worth doing, it seems to me.
Oh, amen. I agree with you.
I'm a little bit of a nut on this. This is why we've talked about the Fermi paradox and SETI in half of my episodes. I just think this is one of the most important things out there. So my final question, which is your bottom line after being the leading researcher in the world on this field for most of your adult life, I would ask you to give me your best guess, an underlined guess. So this is not binding. We know we don't know the answer. What do you think about intelligent life in the universe?
I'm not going to answer your question, Jim, because I don't have an answer. I think we can get an answer by doing this experiments, right? If I told you anything, it would be religion and not science, right? Let's actually do the exploration. I think I've spent my entire career trying to convert the verb to believe into the verb to explore. I think that's the proper thing to do.
You are absolutely right. I'm almost embarrassed for asking you that question because you just gave me the answer I should have known before I even asked it. Well, thank you, Jill. This has been, frankly, an honor to talk to one of my great heroes. And also, I hope, extremely enlightening and educational for our audience.
Well, thank you very much for having me. I've enjoyed the conversation.
Production services and audio editing by Stanton Media Lab. Music by Tom Muller at modernspacemusic.com.